This is the question from 1989 AP Physics B. Now this would be part of AP Physics 2. And the question states that the planar convex lens, and the planar convex means that one of the sides is flat and the other one is curved. And such lenses will have positive focal length, and they're widely used for all-purpose focusing elements. So a planar convex lens shown above in the image has a focal length of, and they give you it is 20 centimeters, the focal length, and is in air, and the object is placed 60 centimeters from the lens. So the distance to the object is given. So the distance to the object and the focal lengths are given. And then state whether the image is real or virtual. And we know from the lessons in my videos that you have heard that when the object is placed farther than the distance of the focal length, so when the distance to the object is larger than the focal length, then in these cases the converging lenses will make real images. That would be the answer for the first one. The image is real, and therefore it's going to be also inverted. And then for the second part, they say determine the distance from the lens to the image. And here I drew the ray diagram for you just to see that the image is going to be real and inverted. I placed the distance. So if I chose this to be focal length, then the image is placed 60 centimeters away from the lens. So I approximated this is about 60, the distance where the object is. And here I have the it's always good to check your work for the answers that you provide. On AP exam, you don't have to draw it on the same image that they provide for you, so draw your images on the different picture. So draw your own picture on the side, don't touch theirs unless they ask you to do something on it. And then for the second part, they ask you to calculate the distance to the image. So I'm going to use the lens equation. So I have 1 over the focal length equals to 1 over the distance to the image plus 1 over the distance to the object. The focal length is 20. Again, you don't have to convert it into meters. The distance to the image, to the object is 60, and the distance to the image we are looking for. So my answer is going to be in centimeters because I did not do the conversions. And then from here, I will see that the distance to the image is going to be 30 centimeters. In my drawing, you see if this was 20 and if that part is 20, so my object, the image of the object would be somewhere between 20 and 40. So it's somewhere like in between. So my image is supporting my answer, which is 30 centimeters. And for the next question, they say determine the magnification of this image. So for magnification, I have the magnification formula, which is negative di over do. So the magnification is equal to negative 30 over 60. And so that gives me negative 1/2. So the image is 1/2 of the size of the object, appears to be. The negative sign again justifies that the image should be inverted. And then for the next question, they say the object initially at the distance df from the lens is placed toward the lens. And on the axis below, sketch the image distance as the object distance varies from 3f to 0. And here I want to go over this quickly before I start drawing the graph. I want to look at the ray diagram and see where my image is going to appear. So when it is at the position of 3f, so here is 1f, this is 2f, and this where we started, the original problem stated, the distance was 3f. So I have parallel to the axis ray going through the focal point, and then through the center, and then through the focal point, and parallel. So this is where my image appeared in the problem that we just solved. For the next one, I have again parallel to the axis, but now my object is at the center of the curvature, which is twice the distance of the focal length. So it's parallel to the axis, through the focal point, parallel to the axis, and then through the center without bending. So again, I get it should appear at the length of the curvature, which is the same twice the focal length on the other side. Then if my image is at the focal point, I have parallel to the axis, through the focal point, and through the center. You see that there's going to be no image. So this one gives me no image. And in the first place, the height of an image was -1/2. That's the one that we calculated in our problem. Here you have the height of an image is equal to -1. -1 of the, we should say magnification. Let's do magnification. So magnification would be -1/2. Here the magnification would be -1, so the height of an image would be the same size as the height of an object, just inverted. And here you would have no image. And in this case, in the last one, we have parallel ray to the axis through the focal point. And then if I have through the focal point, I have to use the focal point on the left side. So I have through the focal point the ray that would go, and then parallel to the axis. And the one that goes through the center would go like this. So it looks like they don't meet on the other side, they scatter on the other side. But on the left side, you will see a virtual image. So here you would have a virtual image. And again, virtual images are upright, they are not inverted. And they appear not where the rays actually meet, because the rays on the other side of the lens don't meet. So this is virtual image. So from this information, we will have the magnification positive and larger. So what I want to say is, based on the lens equations, like if we were plugging in the numbers, the virtual images would have negative DI for the images, and they would have positive DI for when the object is placed farther away than the length of the focal length. If the object is placed between the focal length and the lens, then you have a virtual image and DI is negative. And when the object is placed at the focal length, you get no image. So at the focal length, you will get no image. So right here, you will have no image at all, or we can say image is appearing in somewhere in the infinity. If the object is distance to the object is between so this is my distance to the object. So if the distance to the object is between the focal length and the lens, then my DI, so this is DI that they want me to graph, my DI is going to be negative. So I'm going to have DI negative. And then for the when my distance is to the object is increasing, so when my distance to the object is increasing from the focal length that way, then di is going to be coming from the infinity and approaching the focal length. So it's going to get closer and closer to the focal length. So it's coming from the infinity and approaching the focal length. And here is the focal length. I can also do this through length equation. I can rewrite my 1 over the focal length equation, 1 over di, and plus 1 over do. And I'm gonna solve for equation that will look something as di is equal to m, or let's do k, so we don't have, like, it doesn't look like a slope. So let's do k and do. So this is your y-axis, this is your x-axis, and I want to rewrite it, my equation, length equation, in this form so I can see what relationship it's going to have. So at first I'm going to times each fraction, so I have 3 fractions, by the common denominator, which is di, do, and f. So if I times all of them by this, I'm going to get this expression. And then I want my di to be isolated on the left side. So I'm going to subtract the term with the di on the other side and factor it out. So it's going to be di. And then I have do minus the focal length and equals to do and then the focal length. And then if I divide both sides by the parentheses, I have di is equal to the focal length do over and do minus the focal length. I'm going to analyze the equation that I just came up with. So I'm going to break it into this is equal to I is equal to, I'm going to divide the numerator and denominator by do. So if I divide the numerator by do, I get the focal length. If I divide denominator by do, I can divide do by do, which is 1. And then I have the focal length divided by do. Now, if do, like in my graph, is approaching infinity, if do is approaching infinity, so this, it would be the infinity, then the value of this number becomes really small. Then what's left is the focal length over 1. So that means my graph is going to be approaching the focal length right here. Now, if my do is equal to, so right here, if my do is equal to f, then my denominator, this whole denominator, becomes 0. And I cannot divide by 0, so that's why at this point it would be undefined position. So I have the break line right here on the graph, because I cannot have any value on this line because this is where it's undefined. And then when my do is smaller than the focal point, then I get the number right here that is larger than 1. So I'm going to have the focal point divided by, let's say, 1/2 of the focal point. So this number becomes a 2, and then you have a 1 minus a 2, which is a negative number. And this is when you have the graph staying again negative. So that would be the mathematical lookup at this problem. And I think it gets as complicated as it gets in this case. I'm going to jump to the next section, this question. So the next part of this question says that state whether the focal length of the lens would increase, decrease, or remain the same if the index of refraction of the lens were increased, and explain why. So in our original problem, had object placed 3 times the length away from the lens as the distance of the focal length, so this would be 60, and then this would be 20, and then the ray diagram would be this way through the focal point, and then through the center, and then through the focal point, and then parallel, and it would graph it would give us the image position, right? But then if the index of refraction of the lens is increasing, then when ray gets to the lens, it would have more refracted result as it passes through the lens. So it would be the rays would not go through the same point to graph to give us an image of the object in the same position. So the index of refraction, increasing index of refraction, would give me the focal length shorter than it used to be. So you see, like the blue line passes through this point versus that point. So the focal length would decrease if we increase the index of refraction. So that would make the focal length closer and the image appear smaller as well. So the answer for this question, they say state whether the focal length of the lens would increase, decrease, or remain the same. You would say that the focal length of the lens would decrease if the index of refraction of the lens was increased. And that's all I have for this question. That was FRQ question in 1989 on AP Physics B. Now this section is in AP Physics 2. And thank you for watching, and I will see you in the next video.